10.3 Prediction intervals and variation. A prediction interval is a range of values used to estimate a variable, such as a predicted value of y in a regression equation. Remember when they're talking about predicted value, we've got this notation y hat. So y hat is the predicted value, and a prediction interval is just the range of what the answers could be or should be. Confidence interval is a range of values used to estimate a population parameter. We won't really do as much with confidence interval today as with prediction interval. The objective is to find an interval estimate of that predicted value of y. Imagine if I said we're going to predict the height of the next person that walks in this room. I want a low bound and an up bound, a low number and an upper number. You might say, well, I bet they're going to be between 5'2" and 5'11". That would be your prediction interval. That number should be in between our interval. Requirement for each fixed value of x, the corresponding sample values of y are normally distributed about the regression line, and those normal distributions have the same variance. So remember, anytime we're talking about regression line, looks like that. We're talking about y hat. We're talking about the slope intercept, basically, form of the equation. We've got some really tricky equations here, and luckily we're gonna let a spreadsheet take care of most of the math. But here's the formula for creating a prediction interval. We start by finding the margin of error, marked with E. And you have to be able to find T, you have to be able to find SE, which is the standard error of estimate. You got that big square root. You've got a lot going on in that equation. All right, so let's start with how to find T. You can find this in my spreadsheet that I'm going to show you here in a bit, or you can find T on your TI calculators. If you want to go to second vars, you can do an inverse T value. What's kind of tricky is the example that we will do is in two tails, and we've seen this graph a number of times, but that makes something weird happen. We'll have a 0.05 interval, but you have to divide it by 2 when it's in two tails. And then your second argument is the degrees of freedom. And the example that we've seen a lot, there were 23 data points. So n minus 2 was 21 degrees of freedom there. So this would be your formula you would use. I think it's going to be easier, honestly, if you just use the spreadsheet. X0 is going to be some value of x that is given to you in the problem. Here's your T value I showed you over there to the right. SE is the standard error of estimate, and you can find SE with one of these two formulas. Now again, that's really complicated. If you had to do that by hand, that would be kind of tough, I think. I think it's just going to be easier to look at our spreadsheet. I've got all of this stuff built in. We'll see it when we get there. Example 1, finding a prediction interval. For the paired chocolate Nobel data previously used, we found there is sufficient evidence to support the claim of a linear correlation between those two variables, and the regression equation is this. If a country has chocolate consumption amount given by x equal 10 kilograms per capita, find the best predicted value of the Nobel laureate rate. Predicted value, again, is that y hat number. And so all they want me to do is plug in 10. We're finding the predicted y value if that x value was given to us as 10. Plug it in. You plug in that x value, and we would get approximately 21.5. Nobel laureates, and that was per 10 million people. So we're finding the predicted value, plug in 10. I do want to remind you in these numbers, that number right there is supposed to be 3.3, not 5.5. So you might want to fix that in case you had to type that in. Okay. So that's kind of an easy question. Find the predicted value, plug in 10. Part B is quite a bit harder. Part B is chocolate consumption amount of X equal 10 kilograms per capita to construct a 95% prediction interval for the Nobel laureate rate. We want this prediction interval. So let's check out this spreadsheet right here. And what we need to do is fill in data for the white boxes. All the blue boxes will calculate on your own, but we need to fill in those data. So let's be lazy here. Instead of typing them all in, I want you to go to StatDisk where you can just copy them all in. All right, so remember how to do that. You can go to Datasets and 13th edition, and 16 is Nobel laureate. So pull all that info in. And then what you can do, if you click on the column header for chocolate, you'll be able to right click and copy all those numbers. So I'm going to click right here, right click, copy, and then I'll go here to cell A2 and I can paste those in. I'm going to do the same thing for Nobel, right click, copy, go here. That way I didn't have to type them all in. Most of the formulas are already built in. You've got your x squared, your y squared, your x times y. We need to enter in these numbers. Now, one thing I don't like about this, and Math Excel won't like how it's rounded. So instead of using this, I want to get more than just 2 decimal points. If you go to StatDisk and we go to Analysis, Correlation and Regression, we can do chocolate for our first column and Nobel for our second. We've done this before. Basically, we're trying to find these two numbers, B0 and B1 here. Just got a little bit more accurate. So I'm going to copy that number. And there's my B1. Okay. And X from this problem, it would be different on a different problem, but in this problem it was 10 kilograms, so X is 10. And then we've got our boundaries. Our lower bound and our upper bound looks like 7.8 and 35.3. Everybody with me? Anybody need help? So your prediction interval is going to look something like 7.8 is less than your y is less than 35.3. All right. Now remember our predicted value. Our predicted value is supposed to be in between those two numbers. And our predicted value from above was what, 21.5? Okay, 21.5 fits in between those two numbers, so that's good. This pretty much tells us if our numbers are accurate or not, if our numbers are good or our numbers are bad. But one thing we know is we have 95% confidence that the limits 7.8 and 35.3 contain the value or number. Let's do this. The number of Nobel laureates for 10 kilograms chocolate consumed. We are 95% confident that the number of Nobel laureates is going to be in between those two numbers for 10 kilograms of chocolate. And again, this predicted interval is a range of likely Nobel laureates, so we've got some kind of sense of how accurate the predicted number is. What was the predicted number? 21.5. We've got a pretty good idea, a good feeling that that's accurate. Next, we've got a couple of terms, and it's going to be important that you nail down the symbols here for these terms because they're very similar otherwise. Total deviation is the vertical distance y minus y bar. Remember, y bar is the mean. So it's the distance between the point and the horizontal line passing through the sample mean. Keep in mind, y bar is talking about the mean. Explained deviation is the vertical distance y hat minus y bar, which is the distance between the predicted y value and the horizontal line passing through the sample mean. And then unexplained deviation, also called a residual, is the vertical distance y minus y hat, which is the vertical distance between the point xy and the regression line. All right, I think that's really hard to understand, and so example 2 is going to help. It says draw a sketch illustrating these three things. So I want you to use all of your space as much as you can. And we're going to draw a graph. Okay, so draw the first quadrant of the graph anyway. And we're going to have some line. This is going to be the regression line. So we'll call that y hat equals b0 plus b1x. That's your line of regression. And then what we're going to do is we're going to draw some horizontal line here. And that horizontal line represents the mean, so we're going to call that y bar. Now, over here, kind of in the middle, I want you to find some place on the line and put a dot on the line. All right. And that dot on the line is going to represent the predicted value, y hat. Try that again. Now, directly above it, somewhere, I want you to directly above it make some kind of other point, right? And directly below it, I want you to put a point on the line that represents the mean. So we've got 3 points. They're all vertically in a line. Y hat is the one that's on our line of regression, and y bar is the one that's on the mean, and the other one is just a y from a data point. Okay, we've got those 3 points. So here's what total deviation looks like. Okay. Total deviation is the distance between y and the mean, y minus y bar. Okay. Explained deviation is the distance between y hat and the mean. And then unexplained deviation is the distance from the data point to the predicted value, y minus y hat. So that's a picture of those three deviations. So then we can see that total deviation equals explained deviation plus unexplained deviation, but then there's also something called variation. And so what's going to happen is you're going to have these sums. Okay, total variation is the sum of the total deviations squared. And explained variation is the sum of the explained deviations squared. And unexplained variation is the sum of the unexplained deviations squared. If you think about our picture just shows one data point, but we're going to have a scatter plot with a whole bunch of points. Okay, and so we're not just going to have one data point, we're going to have 23 data points or 57 or whatever. And so variation is the sum of all of those distances. That's what we're talking about. That's what we're looking at. Now, again, you're not going to have to do a whole lot of math here because the spreadsheet's going to take care of a lot of it, but I'm just trying to paint a picture here. That's what it is. The coefficient of determination is given by r squared. And that's the proportion of the variation in y that is explained by the regression line. I think that's hard to understand. You might want to read it again. It is computed as r squared equals explained variation over total variation. So explained variation was the sum of the explained deviation squared. And on the bottom, the total variation is the sum of the total deviation squared. Okay. The value of r squared is the proportion of the variation in y that is explained by the linear relationship between x and y. I think that's really hard to understand. We're going to talk about that again here in a second, though. So r squared is the proportion of the variation in y that is explained by the linear relationship between x and y. Number 3. That picture over there looks an awful lot like the one we just drew a second ago. Okay, it's the same thing. It's trying to show you total deviation, explained deviation, and unexplained deviation. This says find each deviation for that 0.519. The total deviation, okay? Remember, total deviation is y minus y bar. So in this problem over here, you've got some data point, and that's the y number, and the predicted value is on the regression line, and then over here, this must be the mean of 9. So we're taking y minus the mean. That is 19 is my y value, minus 9 is the mean. That's 10. Explained deviation. Y hat minus y bar. Y hat minus y bar. Well, y hat is 13. Y bar is 9. Subtract those, you get 4. That is your explained deviation. Then unexplained deviation. Y minus y hat. (19) minus 13 is 6. Notice that 10 equals 4 plus 6. That makes sense because the total is equal to the explained plus the unexplained. Let's move on. Number 4. If we use the 23 pairs of chocolate Nobel data, we find that the linear correlation coefficient is 0.801. Find the coefficient of determination. Well, in order to answer this question, you have to understand that the coefficient of determination is just r squared. So I gave you a formula for that, but it's probably just going to be easier to just square the r value. We see the r value is 0.801. The coefficient of determination is literally just square that. So here I've got it right here. 0.801 squared is 0.642. Find the coefficient of determination. Done. Also, find the percentage of the total variation in y. That can be explained by the linear correlation between chocolate consumption and Nobel rate. Well, that's not hard because that's just this. It's 64.2%. Okay. 64.2% of the variation can be explained by the linear correlation and in this case it's between chocolate consumption and Nobel laureates. So big picture, think about what we're talking about. All right, this example we've kept coming back to, the same example about the chocolate and the Nobel winners, and we're talking about if I increase my chocolate consumption, does that increase the likelihood of winning a Nobel Prize? Well, those two things don't seem to be related, right? The more chocolate you eat, the more likely you are to win a Nobel Prize. That doesn't seem to make sense, right? Okay, but we know those two variables are correlated. They have a correlation coefficient of 0.8. Okay, those two variables are related, but what we're getting at here is that correlation does not imply causation. All right, that's a different thing. Eating more chocolate does not cause you to win a Nobel Prize, right? But this is attempting to explain that. It's saying 64% of that variation can be explained by the linear correlation. All right, doesn't cause it, but we're trying to explain it away. All right, so we seem to be out of room, but you have more room on your notes. There's one more example that I wanted to do just to make sure you're prepared for the homework. So I've shared this PDF with you on Schoology. Find it if you want to, but here it is. Example 5, the table lists weights in carats and prices in dollars of randomly selected diamonds. There is sufficient evidence to support a claim of a linear correlation, so it's reasonable to use the regression equation when making predictions. For the prediction interval, use a 95% confidence level with a diamond that weighs 0.8 carats. Part A says find the explained variation. So if you go back a couple of slides, I gave you some formulas for explained variation and unexplained variation, but it's got those sigmas, and so it's going to be kind of complicated to do by hand. That's why I've made this spreadsheet. So check it out. The second tab is variation. If you go to the next tab, you've got a bunch of stuff going on. And the first thing we're going to need to do, I believe, is type in those numbers. So I'm not sure you're going to be able to copy and paste them, but there's not that many, so let's just type them in. X numbers 3, 4, 5, 5, 1, and 7. 3, 4, 5, 5, 1, and 0.7. 3, 4, 5, 5, 1, and 0.7. Okay. 523, 1157. 1334, 1405. 5662, 2260. All right. So we've got a lot of extra numbers here. Basically anything in row 9 and above, I want to get rid of all of that. You can put it back later if you need it. I could always take this row and drag it down if I needed more rows, but I only need to go to row 8. So that's all I really want. All right, but you should notice that some stuff's missing here. We need B0 and B1. So if we need B0 and B1, we're going to have to do a linear regression. So you can either do that on StatDisk or you can do that on your TI. You'll need to enter these numbers in though. If you're using a TI, you'll do L1 and L2 and do a linear regression. Or if you're using StatDisk, let's clear out our numbers and we can type them in. All right, but I believe I can probably just copy and paste them. Maybe. Yeah, there we go. All right, once we get them in here, we want to do our regression, column 1, column 2. There we go. So our B0 value, and I wouldn't round off, I'd use as much of it as they give us, negative 1994. And the B1 value, there we go. Okay, so we've got our y hat, which is our predicted value if we plug in the x numbers. And we can see the deviation right here in red. This set of numbers here isn't very useful. All I'm doing here is squaring these numbers because I know when the variation, we're going to have to do the sum of the squares. So this one, if you look at this formula, it's the sum of these h numbers right here, okay? And this one will be the sum of these numbers, and this one will be the sum of these numbers. So you can kind of see where they're coming from. I don't really need these numbers. Here's the deviation if you needed them for each point, but the variation is the sum of these squares of these deviations. So problem A says find the explained variation. Explained variation is this number right here. So it is 16,013,140. 16,013, whoops. 13,140. Then for the unexplained variation is this number over here. Looks like 1,135,082. 1,135,082. I think that's what that said. Yeah, all right. Okay, pretty easy if you can use that spreadsheet. Now part C is a little bit harder because it says find the prediction interval, and the prediction interval is back on that other spreadsheet. So if we want that prediction interval, we're going to go back and pick the other tab, this prediction interval. So I'm going to put the data back in. So let's get rid of that. We can copy this data over. All right. We need to change these numbers. So B0 was this 1994. And B1 7148. And then X comes straight from the problem. They're going to have to give it to you right here. X is this 0.8 carats. That's your X number. And then they give you a lower and an upper. A lower and upper. 2013 and 5437. 2013 and 5437. Make sure you round off to whatever Math Excel tells you to round off to. But in this case, we're going to round off to the nearest integer. Looks something like that. That's our prediction interval. It's got to be in between 2013 and 5437. Now, again, think about what you're talking about here. All right. In this problem, the variables were weight and price. Okay. Weight and price. So which one are we talking about here? Are we talking about weight or are we talking about price? Of a diamond? Is it going to be 2013? I mean, look at your numbers over here. These are your weight numbers and these are your price numbers. Doesn't it seem more like a price number than a weight number? This is the price. Okay, we're talking about 0.8 carats. So think about what we've just found. We've found what we would expect to pay for a diamond that's 0.8 carats. Okay, if you bought a 0.8 carat diamond, you should expect to pay somewhere between 2013 and 5437. Make sense? That's how you know if you were getting ripped off. You're like, hey, wait a minute, this diamond should not cost $8,000. It should be between 2,000 and 5,000. All right, that's what we're doing. Finding a number that makes sense, or figuring out if that number makes sense.